Hi, welcome back to Special Theory of Relativity. In this class, we shall discuss space-like and time-like intervals. To start, let's consider two events A and B. Right? We could look at these two events from a coordinate system which we call as S. All right? We could actually take this as the space-time. We take time along the vertical axis and space along the horizontal axis. For simplicity, we have considered that space is one-dimensional. So we have included only one dimension of space and we have one dimension of time here. All right. This is called space-time, and every point in space-time, right, these are called events. I think we have already discussed these things. To specify an event, right, in one-dimensional or two-dimensional space-time, you need two numbers. You need the x-coordinate, the position. You also need the time coordinate t. Right? You need, let's say, x1, t1. Right? So all the points in this space-time are called events. Right? In a four-dimensional space-time, you would need four coordinates. Since we are taking the space to be one-dimensional, we just need two coordinates to specify an event. Now you consider two events, which we call event A and event B. All right. So these events have coordinates. Let's say that the coordinates of event A in the frame S are given by xa, ta, whereas the coordinates for event B are given by xb, tb. All right. Now we could look at the spatial and temporal separation between these two events. All right. How are they separated in space and time? To find the space separation, you look at the x coordinate of event A, which we denote as xa. For event B, the x coordinate is xb. So their spatial separation is just this distance, which we write as delta x, and clearly delta x is equal to xb minus xa. All right, that's what we have here. Delta x is equal to xb minus xa. We could also look at the time separation between these two events. All right, so this event happened at a time ta, and this event has taken place at a time tb. All right, so this separation, this is ta. This separation is the time separation or the temporal separation between the events. This is what we denote as delta t. Sorry, this is delta tb and this was ta. All right. And clearly delta t is equal to tb minus ta. So we write delta t is equal to tb minus ta. All right. Now we could look at the same pair of events from another frame S prime, which is moving with the velocity v with respect to frame S. All right. So we have got S frame here. We have got S prime frame, okay, which is moving at a velocity v with respect to the in the x direction, which is moving at the velocity v in the x direction. All right. Now, what are the coordinates of these events from the frame S prime, and what are the coordinate separations, or what are the spatial distance and the time separating these two events as viewed from frame S prime? We already know the answer. If we know delta x and delta t, we can find delta x prime and delta t prime using Lorentz transformation equations. Okay, we already know that delta x prime is equal to gamma delta x minus v delta t, and delta t prime is equal to gamma delta t minus v delta x divided by c square. Here, gamma is the Lorentz gamma factor, which is 1 divided by square root of 1 minus v square by c square. These are just the Lorentz transformation equations we are familiar with. All right. Let's now consider two special cases. First, we consider the case where the spatial separation between events in the frame S, right, which we called as delta x, this is greater than c delta t. All right, so the spatial separation is greater than c delta t. Now we know that v appearing here, this is the relative speed between the frames S and S prime. This is always less than c. All right, the velocity appearing here is always less than c. So if delta x is greater than c delta t and v delta t is less than c delta t, all right, so we are subtracting a smaller number from a bigger number here. which means that this is always positive. This is always positive. All right, I'll repeat. We are considering the case where delta x is greater than c delta t. V delta t itself is always less than c delta t. All right, so delta x prime is always positive. Okay, now such intervals are called space-like intervals. Such intervals are called space-like intervals. All right. The reason why we call such an interval a space-like interval is because if delta x is greater than c delta t, then you are not going to find an inertial frame in which delta x prime is equal to 0. Okay, so if delta x is greater than c delta t, delta x prime is always positive. It cannot be 0, it cannot be negative, it has to be positive always. All right, so there is no frame in which delta x prime is equal to 0. There is no such frame. All right, in other words, there is no inertial frame in which these two events take place at the same point in space. All right, it is impossible to choose a system, a coordinate system, in which the events occur at the same place. There's no frame in which the events occur at the same place. There's no frame in which the events occur at the same point in space. All right. For this reason, such intervals are called space-like intervals. We say that event A and event B are separated by a space-like interval if delta x is greater than c delta t. All right. But we see that there's no such restriction on delta t prime. Okay, delta t prime appearing here could be positive, negative, or 0. Right? For example, delta t prime could be equal to 0 if delta t is equal to v delta x divided by c square. Right? So if these two terms are equal, then delta t prime would be 0. All right, we could find the velocity from here, which means that if you go to a frame which moves with the speed v equal to delta t c square divided by delta x. All right, so if v is equal to delta t c square divided by delta x, in that frame delta t prime would be equal to 0, which means that there are inertial frames in which these events take place at the same point in time, at the same time. All right, in other words, there are inertial frames in which these events are simultaneous, but there are no inertial frames in which these events happen at the same point in space. Okay, so it is possible for these events separated by a distance greater than c delta t, it is possible for them to be simultaneous. All right, you just have to go to a frame which moves with the speed v equal to delta t c square divided by delta x in the positive x direction. All right, clearly we see that this speed is less than c if delta x is greater than c delta t. All right, so if delta x appearing here is greater than c delta t, then clearly this velocity is less than the speed of light, and such velocities are possible. All right, you could easily see this. You could just rearrange this as c multiplied by c delta t. Sorry, you could write this as c multiplying c delta t divided by delta x. We are talking about the case where delta x is greater than c delta t. So c delta t divided by delta x would be less than 1, because the denominator appearing here, we are considering the case where the denominator appearing here is greater than the numerator. So if this is less than 1, then we have got v is equal to c multiplied by a number less than 1, which is less than c. All right, so this velocity is allowed, and you are allowed to find a frame. All right, or in other words, there exists a frame in which these events are simultaneous, but there is no frame in which these events happen at the same point in space. All right, events separated by such intervals are called space-like separated events. All right, the second case we consider is delta x is less than c delta t. So the term appearing here is less than c delta t. All right, so this means that you could always choose an appropriate v such that delta x prime is either 0 or positive or negative. In other words, you could always find a frame in which these two events take place at the same point in space, at the same spatial location. All right, but if you look at delta t prime, we see that delta t prime must always be greater than 0 if delta x is less than c delta t. Alright, this can be seen clearly. Just look at this equation. Alright, we are considering the case where delta x is less than c delta t. In other words, delta x divided by c is less than delta t. Okay, now you look at this equation. Delta t prime, for convenience, let's pull out 1 by c from this bracket. So this becomes gamma divided by c multiplied by c delta t, because I have pulled out a 1 by c. Right, here there is already 1 v divided by c square. Because I pulled out 1 by c, this becomes v divided by c. Okay, multiplying delta x. All right, now if you look at this, we saw that we are considering the case where delta x divided by c is less than delta t. So delta x divided by c here is less than delta t. This term is bigger. And v is already less than c. So again, this term is bigger. So clearly, in all cases, the first term is bigger than the second term, and this is always positive. Okay, so delta t prime is always greater than 0 if delta x is less than c delta t. In this case, we say that events a and b are separated by a time-like interval. Right, a time-like interval. Okay, we say that events a and b in this case are separated by a time-like interval. All right, we call it time-like because it is impossible to find a coordinate system in which the events occur at the same time. Right, in this case, we can always find a frame in which the events occur at the same point in space, but we are not going to be able to find an inertial frame in which the events occur simultaneously. In every frame, the order of events is going to be preserved. All right, so if the case is that a happened before b, in all frames, all inertial frames, a will happen before b. Right, in the case where delta x is less than c delta t. So the temporal order, right, the order in which the events happen in time, the temporal order is preserved in this case. All right, so in this case, these events are called as a time. We say that these events are separated by a time-like interval. All right, so that's what we mean by space-like and time-like interval. All right, so let me just repeat it. If you have a space-like interval, if we say that the interval between events is space-like, there's always a frame in which events are simultaneous, but there's no frame in which events take place at the same point in space. All right, no frame in which events are at the same place. There's no frame where events are at the same place. On the other hand, if we say that the interval between two events is time-like, in the case of time-like interval, okay, in this case, there's always a frame in which the events are at the same point in space. All right, or same place. There's always a frame in which the events take place at the same point in space or at the same place, but there's no frame in which the events are simultaneous. Actually, there's another way of looking at the same thing. All right, first we start with a small exercise. I leave it as an exercise for you to find delta x prime squared from here minus c square delta t prime squared. All right, so you could just calculate this. This is equal to gamma square delta x minus v delta t squared minus gamma squared delta t minus v delta x by c square whole squared. You also have to multiply the second term by c square. So this is gamma square c square multiplied by delta t minus v delta x by c square whole squared. Okay, I leave it as an exercise for you to simplify this. In the end, you are going to see that this is exactly equal to delta x square minus c square delta t square. Okay, what we have found is that delta x prime square minus c square delta t prime square is equal to delta x square minus c square delta t square. Okay, what does this mean? This means that this particular combination of spatial and time separations, this is a Lorentz invariant quantity. This is a Lorentz invariant quantity. This does not change under a Lorentz transformation. Okay, we know that delta x and delta t change, but this particular combination of delta x and delta t, it does not change under Lorentz transformations. All right, and this quantity is an important quantity in relativity. This is called the invariant interval. All right, this is called the invariant interval. Invariant interval, we could write this as delta s squared is equal to delta x squared minus c square delta t square. Okay, this invariant interval is an important quantity. All right, you might be learning the importance of this particular combination later on, but we could just try to understand what this means. Okay, we said that the spatial separation between two events, all right, it differs from one frame to another because delta x itself is not invariant. All right, the time separation is also not invariant. Different observers will not agree on what the time separation between two events is. All right, so different observers will not agree on delta x or delta t, but all observers will agree on this particular combination of delta x and delta t. All right. Now, in terms of the invariant interval, we could talk about space-like and time-like intervals. All right, you could just look at this equation. We see that delta s square itself, the invariant interval itself, can be either positive, negative, or zero, right? Because there's a minus sign in between. This could be positive, negative, or zero. All right. Now, what happens is if delta s square is greater than 0, this means that delta x square has to be greater than c square delta t square, or delta x is greater than c delta t. So if delta s square is greater than 0, that means that delta x is greater than c delta t. In other words, in the expression for the invariant interval, the spatial part dominates. The first term dominates. All right, so we call this interval as space-like interval. This is just another way to remember what we have already discussed. Okay. On the other hand, if delta s square is less than 0, that means that the second term is greater than the first term. And this has to be so in all inertial frames because this particular combination delta s square is a Lorentz invariant quantity. Okay, so if the first term is bigger, we say that the interval is space-like. If the second term is greater than the first term, we say that the interval is time-like.